So in the previous lecture we had kind of an intro to algebra, and what we got down to was here. And the story is, if you're able to solve this yourself, this section you'll probably be able to do a lot of what we do in this chapter, but it'll probably explain better to you. If you haven't been able to do this, you need to realize that the maths, the way you're thinking about equations, is not working, and I recommend for you to go this direction. Okay. So an equation says a pair of quantities are equal. And thinking of a weighing scales is kind of pretty good. Now the problem with the weighing scales is we're going to have things that are equal, that are negative numbers being equal, and that doesn't fit very well into the weighing scales metaphor. But this is kind of the idea, and this is just kind of a way for you to think of how if you got a weighing scale and you do the same thing to both sides, they'll stay balanced. So for example, here you've got 2 plus 7 and 5 plus 4 are in balance, and you can add 3 to both sides. So this is of course equal to 9, and so is this. You can add 3 to both sides and it'll remain balanced. Or you could have the amounts on both sides. So you get 4.5 and 4.5, it would remain balanced. Here's another example. So you have 2 apples plus a pear is equal to 200, and this is an equation in weight, or mass even. You can double the amount on both sides, so you could say double the amount of apples, go to 4 apples and 2 pears, the weight of that would be twice of this, would be 400. You could add 50 grams to both sides, it would be the same. Now it's difficult really, I mean, I think there's different things we could talk about, but just maybe for the moment that's where we'll leave it. Well, how do we what's the relationship between these? Well, again, yeah, it's you've got some numbers RVLP, RVLP, yes, and they transpire that when you combine them in this way, that these two numbers are equal. And again, you just got they're basically actually just the same number. They look a bit different. Okay. Right, let's see what we got next. So we must preserve the equality, thus keeping the scales in balance at all times. So you must always do the same thing to both sides. If we do the same thing, apply the same function to both sides of the equation, we keep the scales in balance and create another equivalent equation. So I'm not sure what I was going to draw here, but actually we're going to be using the language of functions. So essentially what we're doing is something like this. So we have this thing, say for example, the 2a plus p, and we have the 200, and they're equal, they weigh the same. Well, what we can do is we can apply a function. It looks like there's two different things, but they're actually the same. 2a plus p is equal to 200. It's the same thing. It looks different, but it's the same. Presumably this will be kind of real numbers. So the kind of things you could do is you could apply the multiplied by 2 function. So, and of course, if it's a function and there's only really one input, there's only one output. Like that's what a function is. You give it an input, produce an output. It looks like two different inputs, but it's the same input. They're equal. They're the same number. So for example, you multiply by 2 and you get, say, 2 times 2a plus p is equal to 2 times 200. And you can do whatever you want. You can apply whatever function you want. Now, why you would do this, who knows, but you could take the square root of both sides. This is a composition. So what you're doing is you're actually essentially applying a function a couple of times until you get something nice. Is kind of the idea. Okay, so this would look like 2a plus p is equal to 200, and then you apply this the same function to both sides. You do the same thing to both sides. So you get 2 times 2a plus p is equal to 2 times 200, we'll write that in as 400. And then again you do the same thing to both sides, because it's not like there's two different things. There's only one object. There's two things that look different, but they're actually the same. And so if you keep applying functions, here's one input, you get one output. Apply another function, you get one output. The two things are the same. So if you do the same thing to both sides of an equation, you get a new equation, another pair of things that are equal. And the thing that will make it always work is apply functions. Multiply by 2, for example, square root. What you don't want to do, and we'll have a look at it. Okay, so I won't do, I won't say too much more here. So you've got this 2 apples in a pear, their mass is 200 grams, and you move the pear over here. What happens? Well, they're not equal anymore. And the reason is you haven't applied the same function to both sides. Essentially, on the left-hand side, what have you done? You've actually subtracted p, and in here, you've added p. You've done different things to the same number. You're going to end up with different numbers that are no longer equal. And so many of the ways, of course, what does this look like? Oh, you've moved over the p. Or you know, in my class, we never say moving. It's nonsense. That's not what is actually happening. You're doing the same thing to both sides. So the key concept here, I think, is if you have an equation, apply a function, and it's pretty much any function, to both sides of an equation to get another one. Now, why do you want to make another equation? Well, we'll see. Now remember, inverse functions are functions that undo each other, and it works both ways. So if you want to undo, say, adding 7, you subtract 7, and if you want to undo subtracting 7, you add 7. So we're going to use functions to get rid of things, okay? Now the question is to identify the thing that you want to get rid of, which we'll look at. Okay, so here there seems to be lots of space. I'm not sure what all this space is for. So what is the inverse of adding a? Subtracting a. So for example here, suppose in all cases you want to find a in terms of the other thing. So what you have on the left hand side here is the +2 function has been applied. You want to get rid of that +2. If you want to get a on its own, you want to get rid of that +2. So what you have to do is identify the inverse of +2. And if you apply the inverse of +2, it'll get rid of it. So like maybe what I wanted to say here was something like, if you do -a after doing +a to any number x, you just get back x. So if I write this, probably a bit more space. So if I do -a, what does +a do to x? It does x plus a. And what does the -a function do? It gets rid of the +a. That's kind of what I wanted to show. So if you want to get rid of that +2, apply the inverse. So what you have to do, the first thing is you identify the +2, identify what you want to get rid of, identify its function. What function is it? It's +2. What's the inverse of +2? -2. And apply the -2 function to both sides. So if you do the -2 function to both sides, it'll get rid of the 2 here. So you just have a on its own. And then apply the -2 function to b, you get b minus 2. Okay. Next thing, what is the inverse of subtracting? So the inverse of subtracting, of course, or the inverse of adding is subtracting, so the inverse of subtracting is adding. They come in pairs. So what are we going to write down? So if you start with a number x, okay, and suppose that you apply the subtraction function to it, excuse me, you get x minus a, and if you want to get rid of that minus a, you apply plus a. So the plus a function applied to x minus a gets rid of the minus a. Okay. So here, if you're looking for a, you identify what you want to get rid of. To get a on its own, this minus 2. So what function has been applied there? The minus 2 function. What is the inverse of minus 2 function? Is plus 2. So apply that function to both sides. The plus 2 gets rid of the minus 2, so you just have a, and you're left with a is equal to b plus 2. No moving involved. Now you say, oh, it's moving, changing the sign. Look, if you want to keep doing that, well, you know, what marks are you getting on your algebra test in school? You know, it's not working. It's the wrong way to think about it. You're better than that. Okay, next one, multiplying. What's the inverse of multiplying by a? Well, it's dividing by a. So I'm not sure what I want to write in here. Well, anyway, the inverse, change that, the inverse of multiplying by a is dividing by a. And so, for example, maybe we'll just do an example. Well, this is our example. And I suppose what are we saying here? If we do division by a after multiplying by a, that's the same as the identity function. Remember, the identity function means you do nothing. In other words, dividing by a gets rid of multiplying by a. So here, again, we're trying to find a on its own. What's stopping a from being on its own? Oh, it's multiplied by 5. So the multiply by 5 function is applied on the left. We want to get rid of it. What's the inverse of multiplying by 5? Dividing by 5. Apply that function to both sides. It gets rid of the multiplied by 5. And then what's b divided by 5? Now you can write it as b divided by 5, but probably this is the way you want to do b divided by 5. Okay. Next question, what's the inverse of dividing? Well, they come in pairs, so the inverse of dividing is multiplying. So if you're looking at this a here, and you say, I want to get a on its own, it's divided by 4. Now you have to be able to identify the thing you want to get rid of and what's happening. Like if you think this is plus 4 or minus 4, we have issues that I would recommend you go to the Academic Learning Centre. They'll give you one-on-one help on that. Of course, you can submit exercises and I'll help you in that regard as well. So we've got this 4 here, we want to get rid of that, but it's a divided by 4. So the issue is that a has been divided by 4. We want to get rid of divided by 4. What's the inverse of dividing by 4? Multiplying by 4. And then we do it to both sides. So if I multiply this by 4, it gets rid of the dividing by 4, just get a, and so I get b by 4, which I might call 4b. Okay. Yeah. Multiplying by minus 1. Now this is a funny one. There's different ways of doing this. So you could say that the inverse of multiplying by minus 1 is dividing by minus 1. That's fine. But actually, the inverse of multiplying by minus 1, another way of looking at it is dividing, say dividing by 2 is multiplying by 1 over 2. So dividing by minus 1 is multiplying by 1 over minus 1. And what's 1 over minus 1? It's actually equal to minus 1. So multiplying by minus 1 is its own inverse. So if you want to get rid of, see this a, it's multiplied by minus 1. If you want to get rid of it, the inverse of multiplying by minus 1 is actually multiplying by minus 1. So do it to both sides. It'll get rid of it there, and then b by minus 1 is minus b. What is the inverse of squaring? Inverse of squaring is square root. So here, now we have to be careful here, because remember, if the squaring, this only works if it's positive real numbers to positive real numbers. If it's real numbers to positive numbers, it's not 1 to 1, because both plus and minus 1 square to give you 1. And if this isn't positive real numbers, it's not onto. So there's a bit of a danger here, right? So what because we're not doing quadratics, I can kind of get away with it. We're just it'll be assumption in the background here. Oh, maybe we shouldn't make the assumption. It's very difficult here for me. So maybe I'll just draw a picture here. So if you don't know that the squaring function is positive to positive, and you're asking the question, say, what number squares to give you a, like in theory there could be loads of them. I'm just going to put in 2 here. So this is real numbers, this is real numbers. Actually, I'm going to make this positive real numbers. And this is the squaring function that isn't from positive but from any real to real. So if you're trying to find the numbers that square to give you a, so your what numbers x square to give you a, you can't quite invert it if it's the real numbers here. It's a little bit messy. So if we were doing quadratics, I'd be able to work a lot here, but in general, when you got a square, you got two solutions. So the picture is going to look like this. Now, if you apply the square root to both sides, the issue is the square root of x squared can actually be plus or minus x, which I'll do down here. But what I'm going to do instead is we'll do the square root of both sides kind of naively. So the square root gets rid of the square, and we apply the square root to a, and then we say there's two solutions, plus or minus. Now, let me do this with an example. Real numbers, positive numbers, numbers that square to give you 9. There's two of them. There's plus 3 and there's minus 3. And the problem here is that the square root does not get rid of the square if x isn't necessarily positive. So say if I look at the square root of 3 squared, that's the square root of 9. Now here you've got a positive number. The square root function goes from positive to positive. That is definitely equal to 3. And look at that, it's equal to plus the number in there. But if you look at the square root of minus 3 squared, now minus 3 by minus 3 is square root of 9, which is 3. It's not the same as minus 3. So the square root does not get rid of the square if the number in here is negative. So there's two ways of going about it. The first is kind of, okay, look at 3 there. That's minus 3. So one way of going about it is you say that this, without knowing anything about x, you say that the square root of x squared is actually plus or minus x, which you can see here. Or I think the easier thing is to say when you have a square, you have two solutions. So just work with the square root, do the square root of both sides, but just note that there's two solutions. So I think we'll be careful like that here as well. Note that in general with a squared, there's two solutions. We want to get rid of the square. What's the inverse of square? Square root. And we do that to both sides. It'll get rid of that square. We apply it to both sides, but we just be careful. There are two solutions, plus or minus. Then the square root, what is the inverse of square root? Well, that one's a little bit easier because you only have the square root of a positive number. A has to be positive there, so you don't get similar difficulties. The inverse of square root is square. So if you want to get rid of that square root, what's the inverse of square root? Squaring. Do it to both sides. Here, a has to equal b squared. Okay. So this is kind of the basics of how we're going to do equations. Yeah. Now, one of the things is these were all done in one line. Here's the thing. Apply a function to both sides of an equation to get another. What we want to do in general is we want to do a series of equations that get easier and easier. So maybe we can't get down to a in one line or 2 lines or 3 or 4 or 5. It takes us a couple. And the thing is we don't know at the very start what functions we're going to apply. We just do one step at a time. So we just keep making the equation easier and easier and easier. We just keep removing things that are in the way until eventually we've removed everything and we have a equal to. So the analogy there is, I'm trying to think, I think he asked a similar question. Remember the laws of sets? That there's more than one way of doing it? Similar story with equations. There's more than one way of doing it. There's different series of functions that you can apply to get there. You want to think in terms of driving. You don't, if you have a very complicated journey across town and you're driving in a car or even walking, you don't think in your head the whole route. Really, you just look, certainly if it's something you're familiar with, you just, oh, I go right down the end of the road and you're on, and then after about 500 meters, oh, I go left here. You don't think, you don't sit in the car and go, okay, this is right, left, then there's like 5 lefts in a row and then I do a right. You don't think like that. Okay. So this is an exercise here and it's for you to kind of do the same. So what you have to identify is what function has been applied to x. So here it's multiplied by 2. You identify the inverse, and then you do the inverse to both sides. So here multiplied by 2 has been done to x. You identify divided by 2 as the inverse and do that to both sides. The divided by 2 gets rid of the multiplied by 2, and you have 3 divided by 2. And so do the same the whole way down there. Okay, now we're going to look at some small algebra things that are a little bit tricky. Okay, so this first thing is about taking out the common factor. Why is this true? Well, it was one of our laws of numbers. So by the way, this a bracket means a multiplied. Well, so yeah, we've basically got an axiom. X times y plus z is equal to x times y plus x times z. That's called the, well, you've seen it in sets. It's also called the distributive law here. So equals, of course, if that's equal to that, it works the other way. So if you have a common factor, you can take it out. Okay, so for example here, both of these are multiples of m. You can take out the common factor of m and be left with t plus s. Okay, now what's going on here? Now we're not going to use the word cancel. Okay, okay, so there's a few different ways of explaining this. So the first way we might explain this is, oh yeah, so there's a big section I normally do on fractions and everything, so I haven't done that. So yeah, okay. So one way of explaining this is using fractions. You might remember from the long distance past that how you multiply fractions is you do top by top, bottom by bottom. And look at this, imagine this is top by top, bottom by bottom. So this, in fact, is equal to a over b times x over x. And now I ask you, what's x divided by x? Now if we go back to our real number axioms, wherever they are, our laws of real numbers, we'll see that a number multiplied by its inverse is equal to 1. This is back on page 106. But this is, multiplying by the inverse is the same as dividing. So x divided by x is equal to 1. Okay, so this number here, this x over x, is equal to 1. So I have a over b times 1. And what's the property of 1? Multiplying by 1 is the identity. It doesn't do anything. Take a number, multiply it by 1, you get the same thing. These words there that you might have used weren't used. ax over bx is equal to a over b. There's another way of looking at it, which would be start with a over b. Be careful now. And I'm going to apply the function multiplied by x to it. So you'd get, and then there's some algebra in here. So if you multiply this x, yeah, it's hard to do this without the earlier algebra. So a over b, probably we can include it here. So see this division, so we're going down to page 106. So if you want to say 5 over 6, this is probably the easiest way to do this. This is the same as saying, well, there's different ways I can say this, but probably the easiest is say this. What do you say? 5/6. 5 times 1/6. Okay. So similar story here. This is a times 1 over b. That is a lot in here. Times x. And then I can also divide by x. And that will be, you can say, so if you multiply this by x, you get ax over b, and then you divide by x, you get, so you have a over b, you multiply by x, and you divide it by x. And of course, dividing by x undoes multiplying by x, so you end up back where you started, which is a over b. That one's probably far harder to understand. So, and then there's another way of explaining this, is where you can divide above and below by x. I'm going to run out of time here, so I'm probably just going to, yeah, I'll keep going here. So the other thing you can do is you can divide above and below by x. So to divide is to multiply by 1 over x. And 1 over x divided by 1 over x, any number divided by itself is 1. So if you multiply by above and below by 1 over x, you're multiplying by 1. And how do you multiply fractions? Top, top, bottom, bottom. So you have ax divided by x, and doesn't dividing by x undo the multiplication by x. And same here, you've got b multiplied by x, also divided by x, so that undoes the multiplication by x, and you get a over b. So it means ultimately you can divide above and below. So you can divide above and below by k. Here you can't do anything. And here you can divide above and below by p. Okay, so these are bits of algebra. This is difficulty.